Welcome to the deep dive. Today, we're going deep into something you use every single day, but probably don't think much about operating systems. You've shared Sistemas Operativos, a Portuguese academic text, and I'm excited to see what we can uncover.
Yeah, there's a lot more to operating systems than meets the eye. I think most people just click and go without realizing the intricate dance happening behind the scenes.
It really is fascinating. We'll explore what an OS does, the tricks it uses to keep everything running smoothly, and the evolution that led to the systems we use today. Did you know that in the earliest days of computers, humans actually had to load programs manually? Can you imagine?
Oh, it's mind-boggling how far we've come. Those early systems were incredibly inefficient. It's like having a high-performance sports car and only being able to drive at 1 mile per hour.
Okay, let's break down this world of operating systems, starting with the basics. What is an operating system?
An operating system, or OS, acts as the bridge between you and your computer's hardware. It manages all the resources like memory, processing power, and storage, making sure everything works in harmony. Without an OS, interacting with a computer would be an incredibly complex and tedious task.
So it's like the conductor of an orchestra making sure all the instruments are playing together in sync.
That's a great analogy. But instead of instruments, we have hardware components, and the OS is orchestrating their interactions to execute the instructions from your software. And one of the key things an OS does is something called abstraction.
Abstraction. That sounds a bit intimidating.
Don't worry, it's not as complicated as it sounds. Abstraction basically means that the OS hides the really complex details of the hardware from you. Imagine you're driving a car. You don't need to know exactly how the engine works to drive it right. The OS does the same thing for your computer. You just interact with a simplified interface, and the OS handles all the behind-the-scenes complexities.
So instead of needing an engineering degree to use a computer, we can just point, click, and go. That makes a lot more sense. Speaking of clicking and going, Sistemas Operativos mentions the importance of data persistence. Even when I turn my computer off, my files are still there when I boot back up. How does the OS manage that?
That's where the file system comes in. The OS uses a file system to organize your data, creating a structure that allows it to store, retrieve, and manage your files efficiently. Think of it as a massive, well-organized library. The OS knows the location of every book, or in this case, every file, and can quickly find what you need.
Okay, so if the OS is the librarian, then the file system is the library's cataloging system. It's what makes sure nothing gets lost or misplaced. But a poorly organized library can be a nightmare. Does the same apply to file systems?
Absolutely. A well-maintained file system is essential for efficient computer operation. If the file system gets cluttered or disorganized, it can lead to slowdowns, errors, and a lot of frustration.
So defragmenting your hard drive is basically like tidying up the library shelves.
You got it. Keeping your file system organized can make a huge difference in how smoothly your computer runs.
This makes me think about how much operating systems have evolved over time. We've come a long way from those early days of manual program loading. What were those early systems like? Sistemas Operativos talks about something called batch processing.
Batch processing was a significant step forward from manual program loading. Instead of having humans load each program individually, they could submit a batch of programs to be run sequentially. It was a way to automate the process and make better use of the computer's processing power.
So instead of waiting around for each program to finish, you could submit a whole stack of tasks and let the computer work through them one by one. It's like having a laundry machine that can wash, dry, and fold everything automatically. But I'm guessing it was still pretty slow compared to what we're used to today.
Oh, absolutely. Batch processing was a huge improvement, but it
Mm.
still had its limitations. The computer was still essentially idle while waiting for input or output operations to finish. It's like having a super fast chef who has to wait for the oven to preheat every time they start a new dish.
I can see how that would be frustrating. You have all this processing power, but it's constantly being held back by these bottlenecks. So how did they overcome those limitations? What was the next big leap in operating system evolution?
The next major breakthrough was the development of multiprogramming, a revolutionary concept that allowed the computer to run multiple programs seemingly simultaneously. This is a major improvement in efficiency.
Wait, seemingly simultaneously, so it was like a magic trick.
It kind of was. The OS would rapidly switch between different programs, allocating small slices of processing time to each one. Because computers were becoming faster and faster, this switching happened so quickly that it created the illusion of parallel processing.
Ah. So instead of waiting for each program to finish completely before moving on to the next one, the OS could jump back and forth between them, keeping the CPU busy and making better use of its processing power. I'm seeing a diagram in Sistemas Operativos that shows something called multiplexigem do tempo do processador. Is that what we're talking about here?
Exactly. That diagram illustrates how the OS divides the CPU's time into tiny slices and allocates them to different programs. It's like a master juggler, keeping multiple balls in the air at the same time.
This time slicing technique must have been a game changer for productivity. Suddenly, you could have multiple programs running each, making progress without having to wait for one to finish before starting the next.
It was a huge leap forward. And this ability to run multiple programs concurrently paved the way for the development of even more sophisticated features, like virtual memory.
Okay, virtual memory. This one always makes my head spin a little. How can a computer have more memory than it physically has? It's like trying to fit a gallon of water into a pint glass.
It's not magic, but it's pretty close. With virtual memory, the OS creates a virtual address space for each program, which can be much larger than the actual physical RAM available.
So it's like giving each program its own private mansion, even if they're all sharing the same small plot of land.
That's a great way to visualize it.
Yeah.
And the OS acts as the clever architect, making sure everything fits and everyone has enough space to work.
But how does the OS actually pull this off? Where does the extra memory come from?
The OS uses secondary storage, like your hard drive, as a sort of overflow space. It swaps data between RAM and the hard drive, bringing only the necessary pieces into active memory at any given time.
So it's like having a filing cabinet where you can store less frequently used documents. When you need them, you retrieve them from the cabinet, and when you're done, you put them back.
Precisely. The OS manages this swapping process seamlessly, so you don't even realize it's happening. It's all happening behind the scenes to ensure that your programs have the memory they need to run smoothly. And this brings us to another major milestone in operating system development, the graphical user interface, or GUI.
Ah, the GUI. This is where things start to look familiar. No more typing in cryptic commands. Now we have icons, windows, and a mouse to click around with. Sistemas Operativos highlights the impact of microprocessors and the decreasing cost of hardware. Did these factors play a role in the rise of the GUI?
Absolutely. The development of more powerful and affordable microprocessors, along with cheaper memory and peripherals, made it possible to create computers that could handle the demands of a graphical interface. GUIs require more processing power and memory than those old command line interfaces.
It's like going from a black and white silent film to a full-color IMAX experience. The technology had to catch up to make those rich, interactive graphical environments possible.
You got it. And the development of the GUI was a major turning point in the history of computing. It made computers much more accessible to a wider audience. No longer did you need to be a programmer or tech expert to use a computer. You just point and click your way around.
This is where things get really interesting, right? The GUI revolution opened up a whole new world of possibilities for how we interact with computers.
Exactly. It was a fundamental shift in the relationship between humans and machines. And as we'll see in the next part of our deep dive, this shift had a profound impact on the evolution of operating systems and the way we use computers today.
Welcome back to the deep dive. Before we jumped into this fascinating conversation about modern operating systems, we were talking about batch processing, that clever way early computers tackled multiple tasks. It was a big step forward, but it reminds me of waiting in line at the DMV. Efficient in its own way, but not exactly what I'd call a thrilling experience. So how did we go from batch processing to the seamless multitasking we enjoy today?
Well, it's a journey of incremental innovation, each step building on the last. Remember, we were just discussing how multi-programming, with its time-slicing magic, allowed computers to seemingly run multiple programs at once. This was a game changer, but there's another piece of the puzzle, time-sharing systems.
Okay, time-sharing systems. Sistemas Operativos mentions CTSS and Multics, both developed at MIT in the 1960s. I'm guessing these were early pioneers in this area.
You got it. CTSS, which stands for Compatible Time-Sharing System, was one of the very first time-sharing operating systems. Think of it like this. Before time-sharing, if you want to use a computer, you had to book time on it, kind of like reserving a conference room. With CTSS, multiple users could access the same computer simultaneously, each working at their own terminal. It was like having your own virtual mind, even though you were sharing resources with others.
So instead of one person hogging the computer for hours, multiple people could work on it at the same time, each getting a little slice of the processing pie. I can see how this would have been revolutionary, especially in research environments like MIT, where collaboration was key.
Absolutely. And Multics, which stands for Multiplexed Information and Computing Service, took this concept even further. It was designed to be a robust, multi-user system, capable of handling a wide range of tasks. While it was ultimately commercially unsuccessful, it laid the groundwork for many of the concepts we see in modern operating systems today. One of the key challenges with time-sharing was ensuring fairness and efficiency.
I can imagine. If you have multiple people sharing the same computer, you need a way to make sure everyone gets their fair share of resources and that the system doesn't get bogged down. How did they solve that problem?
This is where the concept of time slices comes into play. The operating system would allocate small chunks of processing time to each user in turn, rapidly switching between them. Because computers were getting faster and faster, this switching happened so quickly that it created the illusion of continuous, uninterrupted interaction for each user.
So, even though you were sharing the computer with others, it felt like you had your own private session, right? It's like a chef who can quickly move between different dishes, adding ingredients and stirring pots, making it seem like everything is cooking at the same time. I'm starting to understand how all these pieces fit together. Multi-programming laid the groundwork for time sharing, and time sharing, in turn, made interactive computing possible. It's a fascinating chain of innovation.
It is. And these innovations weren't just about making computers faster or more efficient. They were about changing the way people used and thought about computers. Time-sharing in particular fostered a more collaborative and interactive computing environment, which had a profound impact on the development of software and the way we use technology today.
It's like going from a world of solitary confinement to a bustling city. Suddenly, you have this interconnected network of people sharing ideas and resources. Speaking of shared resources, let's revisit the mind-blowing concept of virtual memory. Sistemas Operativos has a diagram that shows these separate virtual spaces for different programs. Can you walk me through how that works?
Sure. As we touched upon earlier, virtual memory is a way to overcome the limitations of physical RAM by creating the illusion of a much larger memory space. Imagine you have a small desk, but you need to spread out a bunch of documents to work on a big project. You might use a system of folders and filing cabinets to keep everything organized, bringing only the documents you need to the desk at any given time.
So virtual memory is like having a giant virtual desk, even if your physical desk is quite small.
That's a great analogy. And the operating system acts as your personal assistant, seamlessly swapping information between your virtual desk and your filing cabinets. It keeps track of which documents are active and which ones can be safely stored away, ensuring that you always have the information you need right at your fingertips.
This reminds me of something we talked about earlier, data persistence. Even when I turn my computer off, the OS makes sure my files are still there when I boot back up. Is virtual memory somehow involved in that process?
It plays a role, but it's not the whole story. Data persistence is primarily about the way the operating system manages files and storage. Remember the file system we talked about? That's the key to making sure your data sticks around even when the power is off.
Right. The file system is like a meticulously organized library, ensuring that every book, or in this case every file, has a designated place on the shelves. But virtual memory helps to manage the active workspace, bringing the necessary information to the forefront when it's needed. It's like having a librarian who can instantly retrieve any book from the stacks, even if the library is the size of a city.
Exactly. Both the file system and virtual memory are essential components of a modern operating system, working together to create a seamless and efficient computing experience.
This has been a fascinating journey through the evolution of operating systems. From those early days of batch processing to the groundbreaking innovations of multiprogramming, time sharing, and virtual memory, it's amazing to see how each advancement built upon the last, paving the way for the digital world we know today. But as we all know, technology never stands still.
Absolutely. And in the next part of our deep dive, we'll shift gears from the past to the present, exploring the diverse landscape of modern operating systems, from the familiar world of personal computers to the increasingly complex realm of distributed systems and cloud computing.
I can't wait to see what the future holds for operating systems. But first, let's take a moment to appreciate how far we've come and the brilliant minds that made it all possible. Stay with us. We'll be right back. Welcome back to the Deep Dive. We've journeyed through the fascinating history of operating systems, from those early pioneers to the breakthroughs that shaped the digital landscape. Now let's explore the diverse world of modern operating systems. It's amazing how they've become so ingrained in our lives, quietly running everything from our smartphones to the servers that power the internet.
It's true, operating systems are the unsung heroes of the digital age. We interact with them constantly, but rarely stop to consider the complexity and ingenuity behind their design.
Let's start with something familiar, personal computers. Sistemas Operativos highlights the rise of PCs and the pivotal moment when graphical user interfaces, or GUIs, entered the scene. It's hard to imagine using a computer today without those intuitive icons, windows, and menus.
The introduction of the GUI was a watershed moment in computing history. It transformed computers from specialized tools for programmers and tech enthusiasts into accessible devices for the masses.
It's like the difference between navigating a city with a detailed map versus simply using a GPS app on your phone. The GUI made computing intuitive and visually engaging. Sistemas Operativos also mentions the role of microprocessors and the decreasing cost of hardware. Did those factors play a role in the rise of the GUI?
Absolutely. The development of more powerful and affordable microprocessors, coupled with cheaper memory and peripherals, made it feasible to create computers that could handle the demands of a graphical interface. GUIs require significantly more processing power and memory than those old text-based command line interfaces.
It's like going from a horse-drawn carriage to a high-speed bullet train. The technology had to evolve to support those richer, more interactive graphical environments. And then came the era of operating system giants, right? The text mentions Microsoft's MS-DOS, which later evolved into the ubiquitous Windows.
The rise of Microsoft and Windows is a classic tale of technological innovation and market dominance. MS-DOS, with its command line interface, was the workhorse of early PCs. But it was Windows, with its colorful icons and intuitive point-and-click interface that captured the imagination of users worldwide.
The text also touches upon Apple and their Macintosh operating system, which took a different approach.
Right. From the outset, Apple focused on creating a visually appealing and user-friendly experience. While they never achieved the same market share as Microsoft, they carved out a loyal following, known for their design aesthetic and focus on simplicity.
So we had this fascinating interplay between hardware advancements, software innovation, and market forces that shaped the landscape of personal computing. And as technology continued to evolve, we saw the emergence of new categories of operating systems driven by the need to manage increasingly complex and interconnected systems.
Exactly. The rise of the internet and networking technologies led to the development of distributed systems, which are designed to coordinate and manage resources across multiple interconnected computers.
Okay, I'm seeing a section in Sistemas Operativos on distributed systems. Are those the systems that power the internet and cloud services, allowing us to access information and applications from anywhere in the world?
Precisely. Distributed systems are the backbone of the modern internet. They enable cloud computing where data and processing power are distributed across vast networks of servers, making it possible for us to access resources and services on demand.
So instead of everything being stored on our own personal computers, we can now access information, applications, and even processing power from anywhere with an internet connection. It's like having a global library at our fingertips.
That's a great way to put it. Distributed systems have revolutionized the way we work, communicate, and access information. And they continue to evolve, becoming more sophisticated and interconnected with each passing day.
Sistemas Operativos also mentions real-time operating systems and embedded systems. What are those all about?
Real-time operating systems, or RTOS, are designed for applications where timing is absolutely critical. Think of systems that control industrial processes, robotic surgery, or self-driving cars. These systems need to respond to events within strict time constraints to ensure safety and reliability.
So it's not just about speed, it's about predictability and responsiveness. A delayed response in a real-time system could have disastrous consequences.
Exactly. In these applications, even a millisecond delay can be unacceptable. Embedded systems, on the other hand, are designed to run on specialized hardware within other devices. They're the brains behind your smartphone, your smart appliances, even your car's navigation system.
So while real-time operating systems focus on time-critical tasks, embedded systems are more about managing the specific functions of a particular device.
That's a good way to think about it. Embedded systems are often designed for specific tasks and have limited resources compared to general-purpose operating systems like Windows or MacOS. They're the silent workhorses that make our modern gadgets and appliances function smoothly.
It's incredible how operating systems have evolved to meet the needs of these diverse and specialized applications. What does the future hold for operating systems? I can only imagine things will get even more complex and interconnected.
The future of operating systems is filled with exciting possibilities. We're seeing a convergence of trends, with systems becoming more distributed, more intelligent, and more interconnected. The rise of the Internet of Things, where everyday objects are connected to the Internet, presents new challenges and opportunities for operating system design.
So we might have operating systems managing entire smart homes, coordinating fleets of autonomous vehicles, or even optimizing energy grids across entire cities.
Absolutely. We're also seeing a growing emphasis on security and privacy as operating systems manage increasingly sensitive data and control critical infrastructure. As our dependence on technology grows, so too will the importance of robust, secure, and adaptable operating systems.
It's mind-boggling to think about how much our world relies on these complex systems that operate largely behind the scenes. This has been such a fascinating deep dive into the world of operating systems. We've covered so much ground, from their fundamental definition and historical evolution to the incredible diversity of modern systems and the exciting possibilities that lie ahead. I want to thank you for joining me on this journey, and thank you for listening.